Hi everyone, welcome to today's topic. So this is the actually topic number 22, and for topic number 22 I have chosen the Borane cluster. So this is from main group element, and this will be a one short revision of that cluster, or the weight rule, I will say. So depending on that rule, actually, we will find out that what are the types of structure of the Borane clusters are actually present, and how can we determine the structure. So that kind of questions are actually very common in the exam, CSIR-NET exam. So you have to have that idea. So let's not talk about the introduction much. Let's start today's topic. Okay. So this will be very helpful because it will be mostly the question solving session. So we will solve it, solve the structures and the polyhedral electron count. These things are actually there. So, so please keep patience and watch the video carefully. Okay. So the weight nomenclature for borane. I will say weight. I can say weight rule. Weight rule for borane. Okay. So the boranes. What is first we have to understand that what is a borane, right? So before that, what is boron? Boron, we know that it is a what P group element, right? What are P group element actually? The elements which has their valence electron or last electron filled in the p orbital. Okay, so boron has 1s2, 2s2 and 2p1 configuration. Okay, so it is in the third group in periodic table. So lithium, after lithium and beryllium, then boron comes. After that, carbon and nitrogen, oxygen, fluorine, neon. Okay, so that is the thing, and this is 3, 4, 5. Total electron I am saying 6, 7, 8, 9, and 10. Okay, these are total electron, and valence electron will be here will be 1, here 2, because 1s2 electron is in the lowermost orbital. So it is not, it will not be counted in the valence electrons. Okay, so for boron it will be 3, carbon we know 4, right? And here nitrogen case 5, in the outermost cell the electron is there 6, there 7. Here these are inactive, so let's not talk about these. Okay, so this is 2s1, this is 2s2, this is 2p1, this is 2p2, this is 2p3, this is 2p4, and fluorine is 2p5, right? So here we are talking about the boron. So 2p1, last electron is in 2p1. Okay, so 1s2, 2s2 and 2p1. This is the electronic configuration, and the valence electron is total 3. Total electron is 5, but valence electron is 3. Fine. This idea and the idea of that series, also the group wise, the what are the elements, that is actually needed here. Okay, to calculate the or to determine the structure of the boranes. In the latter part, the other elements also will be included here. You must be thinking that why we will remember that other the electron number of other element or the periodic table, I mean to say, because here only we are right now we are saying that borons, but there will be heteroborons. I will come to that part also. So before this all actually, so boron we know now, p block element having valence electron 3, and this is the electronic configuration. Fine. So boranes, what are boranes? Boranes. So boranes are boron hydride. Okay, boron hydride having cage-like structure. Okay, so borons are boron hydride having cage-like structure. Fine. Depending on the number of boron and hydrogen, because boron means boron plus hydrogen. This is boron, borohydride, right? So the number of depending on the number of boron and hydrogen, various clusters can be formed with defined structures. So these actually we can calculate with Wade rule, and we say it as Wade nomenclature. Okay, so this is the table. This is very important table. So when the general formula of the boron hydride is like that, that BnH10 2 plus, that time we will call it supercloso, and it will be counted as N minus 1. What is N minus 1? It will be helpful in the calculation purpose, or when we are actually solving the, let's say, determination of any structure, like any formula will be given to you and you will be asked that what is the type of structure of this boron cluster. Okay, that time this is needed. Okay, and this is actually I think, yeah, that is fine for now. So hypercloso when BnHN only, when BnHN 2 minus, that time closo. Nido is BnHN 4 minus, like that way. So means the changing of the charges. See, you can relate. So minus 2, minus 2. If we add the minus 2, but here it is actually a defined case. Let's not think about that. But here, if we add minus 2, here also if we add minus 2, okay. Here also if we add minus 2, okay. So supercloso, hypercloso, closo, nido, arachno, hypoclado. These you have to remember. Fine. Okay. So short trick I can tell you here. So let's bear the way. Okay. Fine. So this is SH. SH we know thiol group, right? So SH and cyanide CN. Fine. Now HC, aromatic heterocyclic compound. Okay, like that way you can remember SH thiol, CN cyanide, and AHC aromatic heterocyclic compound. Okay, this is a short trick actually, and the general formula you have to remember. Fine. You can remember it like in a series, how the charges are actually changes. BNHN is constant, right? So let's talk about now how can we calculate or determination of structure. So the step 1 is calculate the total number of electrons for a complex, that is called total electron count or TEC. How can we calculate? TEC will be valence electron of boron, as we are talking about BNHN kind of thing. Okay, let's be any charge is there. So valence electron of boron, this into N, obviously number of boron, plus valence electron from hydrogen, total, as a total. Okay, so obviously number of electrons from hydrogen is 1, and we have to multiply with hydrogen number, plus if negative charge is given, that will be added, and minus overall positive charge on the complex. Okay, this is simply now the formula. Now step 2 is the polyhedral electron count. Okay, so these actually we can show it like this is actually the same thing. We can write that Kenilton electron pair, not electrons, electron pair. Okay. So PEC is also called skeletal electron pair. Fine. So PEC can be calculated by this formula. So if we know PEC minus 2 into N, N means the BNHN units. So BH units, number of BH units. When we take the common BH, okay, how many BH units are there? Okay, this will be called the N. Okay, fine. Now, or we can say how many B, because B is masked here. B should be inside the bracket. Step 3 is the polyhedral electron count will be divided by 2. Okay, PEC by 2, right? Now what? The value, let's say we got X value. Okay, now we have to express the X value as the N with respect to N actually. Okay, so please arrange this value, this X value, according to the respective N values. Respective N values means the BH unit is actually different for every clusters. When we see the examples, you can understand it in a better way. So that will be N will be different for the all structures, right? So the respective N value which you are actually given, with that actually you have to arrange this X value, this value. Okay, let's say we got, let's say for this is B2H2 is given. Let's, for example, this will be equal to what? BH whole 2. So N is 2 here. Fine. And after polyhedral electron count by 2, after dividing, we get 3, let's say. I'm assuming. So this is X now. So we have to express X with respect to the N. How? It will be 2 plus 1. Right? If it is means it is N plus 1. So go back to the table again. So if it is N plus 1, that means if it is N plus 1, that means this N plus 1 means closo, right? You can see in the table, this is closo. So it will be the closo structure. So the answer will be, when you are asked that we need the answer, that what will be the structure of the cluster. This will be actually the closo for 3, closo. Okay. So let's take the example. Okay. So let's say this B9H15. Fine. First, what we have to do? The calculation of PEC. Fine. The total electron count. Second, okay. So first step is TEC, that is fine. But before that, we have to arrange it such a way that we can take the BH unit inside a bracket, or we have to here we have to somehow take the BH unit. Okay. So we have to actually write this formula like this. We have to take the BH unit as common. We have to find out that how many BH units are present. Okay. So it will be 9, right? 9 we can take from H. So BH unit we know it need. It will be whole 9. And how many H's are left? H. So 15 minus 9, that will be 6. Like that way we can write. Right? So N is here. So why we are doing this? We need to find out the N. N is here 9. Fine, get it? Now step 1 is calculation of PEC, and we know boron has 3 valence electron, right? And so TEC will be, so boron has 3 valence electron, 3 into 9, 9 boron units, boron is there. Borons are there, and hydrogen is 15. 15 into 1, I am writing 15, and no charges are there here. Okay, fine. Now TEC will be 27 plus 15. That will be 42. Fine. Now the next step is step 2. Calculation of PEC, polyhedral electron count or skeletal electron pair. Okay. PEC will be 42 minus 2n. N is here 9, right? So 42 minus 2 into 9 means 18. So this will be 424. Fine. Now the third step, this is PEC by 2. We have to calculate. So PEC is 24. PEC by 2 means 12. This is the X value which I talked about in the previous slide. So we have to express this 12 with respect to the N value, means 9. So it will be obviously 9 plus 3, right? So N plus 3 means N plus 3 is what? It was closo, nido, arachno, right? So closo means N plus 1, right? Nido, after closo it is nido, means cyanide CN, then aromatic heterocyclic compound. So CN after nido, then nido N plus 2, and then aromatic heterocyclic compound. Then comes aromatic, means N plus 3. So N plus 3 is arachno. So the structure of cluster will be arachno. Fine. This will be the answer. So here the table also I have given. So N minus 2 is supercloso, means thiol SH cyanide aromatic heterocyclic compound. Okay. Now the simple trick I will tell you. So you don't have to calculate the TEC and PEC for each cases. There is a trick. If you can remember it, then that will be easy for you. But if you are confused or you are making mistakes again and again with that trick or with that simple rule, I will say trick. This is so. If you are making mistakes again and again, so I will say that the preferable way should be the after counting the electron only you should calculate in the exam. But these tricks are actually you should know, okay, to calculate in a more efficient way or more easy manner. Okay. So what I'll do here, let's just see that if we, this is actually uh, the different thing here. Okay. Exception, this is here, this you have to remember. But for the rest cases, if you see the power, only focus on the power, okay, because that is only the thing which is changing, right? If we multiply it by minus 2, this will come. If we multiply it by minus 2, this will come like that way. And see, if we multiplied, sorry, if we divide this, if we divide each power, I am saying again, okay, you can be confused with that, okay. So for each power, okay, for each power, these two are actually, this will be can solve, but the hypercloso is actually we can say is a special case. So for this, power is plus 2. If we divide each and every power by minus 2, it will be what? Minus 1. See, in minus 1. So what value we got after this division, we will just add with n. Fine. So let's take the, this is the exception. This we will forget. And let's say this one. Closo. So power is minus 2. And we are dividing it with minus 2. We will get 1. So n plus 1. See. Nido. BnHn 4 minus, so minus 4 by minus 2, it will be 2. So nido, and like the same here also minus 2, it will be plus 3. Here also minus 2. After division, it will be plus 4. Like that way, this is happening. So how it is helpful? It is helpful because if we are asked, we are given the general formula and we are asked that what is the structure of the cluster. We don't go towards the electron counting and all. After seeing the structure only, if we can take the common, the BN unit, BH unit as common, let's say N, okay, and other H, let's say some X amount of H is there. Fine. So the process I am with example, I will take some examples, but here in a short manner I will explain to you. So let's say B N H something. Let's say Y is given. Okay. So Y is N plus X. So I am taking, obviously I have to close the bracket, the BH we have to take common, or we have to just take it differently, right? So BH whole N and HX is there, and we know if we can remove H, the minus sign should be there, right? Let's say we are adding base. Base, what we'll do in acid, let's say 1 HA acid is there. If we add base, okay, base will abstract the proton and A minus will be there, right? So after removal of H plus, minus sign will be there for the rest of the formula. So here also we are taking the same thing, that we are removing the rest H's, the which are not inside the bracket, okay, and we are taking that much negative sign. Fine, clear? So here this will be the and you are asked the structure. So X minus, what is the, I don't know the value of X, so we divide it with minus 2, and what value we can get, with that only we can say that it is closo, nido or arachno. Because if we get 1 here, it will be closo. If we get 2 here, we will say it is nido, and if we get 3 here, we will say arachno. Like that way we can calculate. Very easy technique this is, right? So for example, if we take this, the same example which I was calculating, right? I was calculating the total electron count, then the PEC, right? So so let's just now try to solve it by this trick. Fine. We just first have to isolate or take the common, the BH unit. Okay. We have to take it. So BH 9 BH. Okay. So how many H's are left? 6, because total 15, right? Now we have to remove the H plus, 6 H plus. So how many negative charges will be there? 6, right? Now we don't have to do nothing. We have to do nothing actually. So we have to divide it with minus 2 and we will get 3. And we know for the arachno case, we will get 3. So n plus 3 means arachno. Arachno will be the answer. And if we remember that when we are actually calculating this also, when we are calculating that time also we can get this one, arachno, right? So we have done it correctly. Let's take another example, B2H2. This is diborane. This is very famous example. Okay, let's just solve it. First BH unit, right? It will be whole 2 and H4 will be outside. Now BH whole 2 and 4 minus, right? Now we will deal with only the minus 4 and we will divide it with minus 2 and we will get 2. That means it is nido, right? It will be nido, n plus 2. So this will be a nido borane. Nido borane. Nido will be the answer. So we will solve again where negative charge is present from the beginning. Okay. So what we will do? We'll do nothing. Just add the negative charge, right? So first B5H5 and H3 and whole negative is there. So BH unit is 5 and H3 is in outside and overall negative charge is there, right? And after removal of 3 hydrogen, we can get 3 negative charge. So total, it will be what? It will be BNHN and 4 negative charge, right? Now, if we divide minus 4 by minus 2, it will be 2. So, it will be nidoborane. Simple, right? This is nothing but this BH unit is nothing but BNHN. This means B5H5, right? So, this is simple. If we can solve it in a easy manner and you are not confused about the trick, you can obviously take it, right? But if you are confused about it a little bit also, you will solve it only after taking the total electron count. Fine. Now I have taken one CSIR-NET question. So according to wave theory, the anion, this anion will adopt what structure? See, the straightforward questions are asked from this chapter. You have a proof now. See how easy examples, easy questions you can see here. So this is this one. So BNHN, 12 B units are there or boron. So 12H is also there. So this is the only the structure, right? And 2 minus is there only. So if we divide 2 minus with 2 minus, it is 1, and we know we can get 1 for this n plus 1 and it is closo, right? Simple. See here, and I will solve you again with TEC. Not for every cases, for this case I will solve you. So TEC, total electron count, will be for this case what? 12 into 3 for boron plus 12 into 1 for hydrogen, and we will add the negative value, right? And we will subtract the positive value. Here negative value is there. So this will be the total electron count. So 36 plus 14. It will be 15, and TEC will be, see how difficult this is because calculation part is there na, and here the making mistake is actually very frequently, you can make mistake. Okay, so 50 minus 2n, 2 into n is here what? N means 12, BH unit 12. So 50 minus 24, it is 26, and we have to now third step, 26 by 2, that is 13, and now we have to arrange it with respect to n. N is here 12, so 12 plus 1, see here also we got closer, so we are in right track. Fine. Now the second example is the same kind of example is actually there. So B6H6 2 minus, oh, what is the question actually? So the number of bonding molecular orbitals and the number of available skeletal electrons. They want to know that, not the structure. Okay. So both, knowing both the things, both the processes is very important. See. So the number of, okay. So we know how to calculate TEC and this. Fine. So the PEC, I have told you, this is equal to the skeletal electron, not electron pairs. This is pairs, right? And the molecular orbital, this will be equal to actually the molecular. because in the molecular orbital only the skeletal electron pairs are there. So this is the molecular orbital. This idea you have to understand. Okay. So first the TEC, total electron count. For boron 6 into 3, for hydrogen 6, for negative charge 2, right? 18 plus 8, it will be 26. Fine. This is TEC. Now PEC. PEC means what? PEC means that this one. 26 minus 2 into n means 6. 26 minus 12, that is 14. PEC is 14. Okay? I'm getting it wrong. Okay, 40, right? So, see the available skeletal electrons. Okay. And now what we will do? We will do yes, this is actually polyhedral electrons because what we will do in the third step? In the third step, we actually divide the PEC. Where is my pen? In the third step, what we will do? We actually divide the PEC by 2, right? The third step is PEC by 2. There, 14 by 2 means 7. What is 7 now? 7 is the molecular orbital. Is the molecular orbital. Okay. And this is the skeletal electron pair. This is the skeletal electrons, the PEC, and this is molecular orbital. This is actually wrong. So PEC by 2. PEC by 2. Okay. So molecular orbital. Okay. So molecular orbital will be 7 and the PEC actually equal to the skeletal electron. Or this is the skeletal electron pair. Skeletal electron pair. Okay. If we multiply with 2, because pair means 2 electrons each, right? So 7 into 2 is also 14 and we can also write here also the skeletal electrons. Right? So skeletal electron will be 14 and the molecular orbital will be 7. So 1 should be the answer. Fine? Clear? So PEC. PEC is nothing but the skeletal electrons and PEC by 2 is the molecular orbital or skeletal electron pair. Electron pair. Don't be confused. Okay? Fine. Next is the heteroborans. This is very important. So heteroborans means with boron some heteroatoms are also there. Okay. Like the other group elements can be there. Other group elements and sometime transition metal is also there. See, first we will know about the other main group element. Okay. So depending on their valence electron of the heteroatom, we can actually compare any heteroatom with a combination of boron and hydrogen. What I mean to say that any heteroatom is given. Depending on its valence electron, we can compare that heteroatom with a combination of boron and hydrogen. And so that it can be replaced with combination of boron and hydrogen. Specific combination of boron and hydrogen. How? See the table. These are, let's say, the elements. This is group 3 element. This is group 4 element. This is group 5 element. This is 6 and this is 7, right? All are p blocks. So electron count is, we know, for boron 3, and this is same for the all group. Group means like this is group and this is series, right, in that periodic table. So boron, aluminium, this is like that way: boron, aluminium, gallium, indium, thallium. Okay, so like that way. So I am just writing here for the easy to write it was. Okay, and less space actually needed for it. So electron count is 3, and this is actually boron, right? So there is no boron fragment. For group 4, which are having electron count 4, this is carbon, silicon, germanium, tin, and lead, Pb, right? So 4 means 3 plus 1 is 4, and we know boron has 3 and hydrogen has 1. Means we can write as BH. This is nothing but 3 plus 1. And for 5 means group 5, nitrogen, phosphorus, arsenic, antimony, bismuth. 5 means boron 3 and 2 hydrogen, right? So 3 plus 2, you see, 3 plus 2, boron and hydrogen. So same for 6, this is BH3. For 7, we can write BH4. Like that way, when any heteroborons are given, we can replace that heterocarbon or hetero element with the BH units. Let's take an example and see. Okay. And before that, before taking an example, let's see that transition metal and borons. So again, depending on the valence electron or the total electron count actually for the complex, we can actually compare that with borons. Same way. But we have previously also read in the isolable analogy that when we are comparing a transition metal and any main group element, the 10 should be added with the electron count of main group element. Means if for the transition metal, let's say 13 is the electron count, we will compare it with the 3 for a main group element. This will be compared with 3. 14 will be compared with 4, and 15 will compared with 5. 16 will compared with 6, 17 will compared with 7. So everything minus 10, like that. Okay, for any p block element or main group element. Fine, for the transition metal only. And now, so we know 13 will be compared with 3, and we know 3 electron means boron, which we have just read it, right? So 14 means 4 and BH, 15 means 5 and BH2, 16 means 6 and BH3, 17 means 7 and BH3, like that. Okay. So I hope you have understood this. This is very easy, right? And interesting also. So this example I have taken as the carboboron. Carbon is present, right? This is called carboboron. So here also the same formulas and same thing are applied, but before that we have to convert it to Borane cluster. Okay. So carbon is, we know, carbon 4 electrons, so it is BH unit. So carbon means BH whole 2, right? And B4 is there, H7 and minus charge is there. Fine. I am not changing anything in the first step. This will be equal to, so the total number of boron is now 4 is there, 2 is there, so 6. Total number of H is 7 plus 2, that is 9, and negative charge. See, we have converted it to boron. This is boron only. So from a heteroboron, we have converted it to boron. Now we know the trick, right? We know the trick. What trick? This will be equal to BH unit we have taken out, and this will be 6. And how many H is there? 3 H is there, and 1 negative sign, overall negative sign is there. Fine. And this will be compared with BH 6, and H will be gone. So it will be overall 4 negative, and 4 negative means by minus 2 it will be 2, and 2 means nido. So structure will be nido. And if you are asked that polyhedral electron count or that kind of molecular orbital or skeletal electron pair, that can be the question, right? So for that case also, we will just count down the electrons from that. If you are confused here, you can calculate from this step also. Okay. From here also you can calculate, like you know that for carbon 4 is the total electron, right? So 4 into 2 plus 4 into 3 plus 7 and 1 negative is plus. This will be the total electron count, PEC. Okay. And PEC we know, PEC means that TEC minus 2N, right? So for N actually you have to find out this. Okay. Fine. Now the second example I have taken, transition metal fragment is also there. Okay. So we can simplify this taking CpNi whole 4, right? We can write that because all are 4 and BH4. I am writing like that. Fine. First, I have to compare this fragment with, I have to actually replace this fragment with any BH unit. So for that, first the total electron count I have to take, because this is not known, right? So Cp means 5 and Ni means D8 means 10, right? So this will be 15. So 15 means it will be comparable with main group element 5 with total electron count 5. This is actually nothing but the BH2. B means 3 and 2H. 3 plus 2 means 5. So we can replace it with BH2. This whole 4 will be there. Please watch carefully. Whole 4 will be there, but only in the place of CpNi, we can replace it with BH2. So BH2 whole 4 now, and BH units are there. Now we have to see that how many B and how many H's are present. H are present. So B4 and 4, B8, and hydrogen will be 8 and 4. That is 12. Yes, 12. Now BH unit is 8 and H is 4. Means BH whole 8, 4 minus 4 minus 2, that is 2. That is also Nido. Okay, answer is here also Nido. Okay, and the total electron count you can do from here also, because the number of N actually needed in the PEC formula. Okay, so that is the thing here. Now coming to the question part. So the number of skeletal electrons present, skeletal electrons, not electron pair. Please read carefully the questions. So skeletal electrons present in the compound, this, and this. 3 boron compound clusters are there. 2 are carboborans and another one is boron. Okay. So first, for the first case, this is C2, B3 and H5. Let me just see that. Okay, fine. So, okay. So for the in the case of C2, I know that I can replace C2 with BH. So BH whole 2 and B3H5, right? Now what? Now the total B is now 3 plus 2, that is 5, and total H is 2, 7, right? 5 plus 2, 7. Now BH whole 5 and 2H, it will be also, we can write as 2 minus, and 2 minus means if we divide it with minus 2, it will be 1 and it will be closure. Okay. We don't want to know the closure now. We need to do the total electron count, right? Total electron count will be boron 3, hydrogen is 7, and no negative and positive charge. So this will be the total electron count. This will be 22. So PEC will be 22 minus 2 into N means 5. That is 12, right? And we are asked that skeletal electrons. So 12 will be the skeletal electrons. If we divide it with 2, that will be the skeletal electron pair or number of molecular orbitals. Okay. So for the first case, it will be 12. So see, both options are actually 12. Okay. So these will 1 and 3 will be not the answer. This can be the answer. And see, for this 2 and 4, both cases, the second one has 14 skeletal electrons. So we don't have to actually calculate that because for each cases 14 is given. These kind of tricks are actually needed to solve question in a faster way. Right? So now we will only solve this one. B5H9. Okay? B5H5 and H4. Right? So means this is n equal to 5, right? BH unit is 5, n equal to 5. Fine. Now PEC will be 5 into 3 plus 9. That means this will be 24. Okay. And PEC will be 24 minus 2 into n means 5. That means it will be 14. So the answer, the skeletal electrons will be 40 for the third case. So 12 and 14, sorry 14 not 40, 14 is in the second option. So it will be the correct answer, this one. Fine. Now again the CSIR-NET question is there. According to the Wade's rule, the correct structure type of this and this. See, the transition element fragment is also there and the boron unit. Fine. And here only the, oh no, not only, here also boron is present. Okay, fine. The two boron is present. Okay, fine. So now what we will do is that for the first case, let's say, let's write eta 5, T5, H5 is there, and B4, H10, H8. Okay. So first we have to convert it to a BH fragment. Okay. So cobalt means we know this is a D7 system. We will take 9 electrons for it and 5 for the CPD. Fine. So 14 electrons as a total. 14 electron means we can compare it with 4 electron species in the main group, and this is not nothing but carbon or BH. Clear? So we can replace this whole thing with BH. This will be BH and B4H8. As a total, we can write B5 and H9. Clear? We want to know the structure, so we will apply the short trick. What is that? B5H5 and 4 minus the other hydrogens, right? And it will be 4 minus by minus 2, it will be 2, and it is Nidu. So first one will be Nidu. This is in the case of 2 and 4. These are not the correct option. So now the second case, this is Mn eta 2 B3H8. Fine. And CO4. Fine. So we know that total electron count for this, what will be the total electron count? Right? So for that actually, this is nothing but this is not a boron cluster the question, but it is only the acting as a ligand here. Here is also a ligand. It is what I will do. What I will do here? What I can do here? I can take the Mn and CO whole 4 as a fragment of transition metal part, and the rest will be for the boron complex. I'm thinking, okay, let's just solve that like that, and then we will understood. Okay. So Mn means D5, so 7, and CO, CO means 2 electrons, so 2 that will be 8, and this is 15. 15 can be compared with 5, and this will be now this will be uh, CH or BH2. BH2. So here this will be BH2, and where what is present? B3H8, right? So total B will be 4 and H will be 10. We can write it like B4H4 and 6 minus. This can be arachno, right? This will be arachno. Which option? Two option is arachno, but let me check again that it is. So it will be like okay, Mn has 7. Yes, like that way only we can solve. There are no other ways actually. Yes, no other ways. So this is actually the correct way. So if you are confused with that, just forget about that, because this is also here acting as a ligand. So we are just assuming it as a ligand, boron ligand, and the rest means the Mn and CO4 will be taken as a part of transition metal. Okay, so we will solve it for the Mn and CO4, the electron count, and the rest thing will be there for the calculation part. This one. Okay. So MnCO4 I have taken. This will be the electron count, and we can compare it with BH2. And if we put the BH2 here, this will be the total B4H10 and B4H4. 6 minus will be there now. So it will be compared with N plus 3. Fine. N plus 3 means or 3. Here we answer is 3 means arachno. Clear? So the 2 will be the answer. Now Zintal ions. This is also a very important thing. What is this? Ionic cluster of main group element without ligand. For example, examples are SN9 4 minus. See, here no ligands are given, and these are main group element. Okay. So for these cases, for the calculation of that, we can compare it with again boron, right? We have to see that in which group element these are, and we can compare it with BH unit. That is fine. But if we are asked to calculate the total electron count and the other things uh, for that actually, so if we are actually counting the total electron count and the PEC, so from that process to know the structures, actually we have to follow this formula. So nothing defined is there, only in the it was the n plus 1 actually for the closure. So only here 4n for the case of in the place of n there will be 4n and plus 1. So 1 will be there and multiplied by 2, so 4n plus 2. Okay, 4n plus 6, like that way it will be the thing. Okay, so only the difference is this one. But if you are asked that only structure, if you are asked, you can compare it with the boron units and you can easily solve that. Okay, so here is a question. So I will solve here also like this one. Let's say teen SN9 4 minus. Okay, so teen is in which group? Please tell me. It is in group 4, right? Carbon group. Okay. Where actually we have read it? When we are reading heteroatoms. Listen, team, in carbon group, right? So electron count should be 4. You have to keep that in your mind. This is the last question actually. Please see carefully. So before that, here, so tin is in carbon group. It has electron count 4. So 4 into 9, that is, sorry, plus 4, negative charge. So 36 plus 4. Okay, that will be the electron count. So forget about it. And 4 means it is BH, right? So we can compare it with BH whole 9 and 4 minus, right? So B9H9 and 4 minus, it will be what? 4 minus will be divided with 2 minus, and it we will find 2, and it will be nidoborane. Like the structure of gentle ion will be nido. Fine. So now take that example, that addition of 2 electrons to the bismuth cluster, this one, result in a change of structure, the type from what to what. So they are just adding 2 electrons to the bismuth cluster. Okay. Let's just find out what was before addition, what was the structure. So bismuth is in which group? Arsenic, antimony, bismuth, right? Nitrogen group. Nitrogen, phosphorus, arsenic, antimony, and bismuth. Yes. Okay, fine. So this is in group 5. This will be BH2. Carbon. After carbon, this nitrogen is there, right? So it will be BH2, obviously. 5. Yes, BH2. So we can replace Bi with BH2. This is 3 plus. So BH2 whole 5, 3 plus. Fine. This will be what? BH5 and so 10 hydrogen was there. So 3 plus was previously there, and we have to subtract 5 hydrogen from there, because here only we have taken 5 hydrogen. So 5 hydrogens are left. So here that will be the case. So it will be BH whole 5, and I hope you have understood this. So till now we have solved many questions, right? So you can solve it. So minus 2 by 2, minus 2, it will be 1, and it will be closo, right? This will be closo. So 1 and 3 can be the answer, between 1 and 3. Let's just find out the second one. Second one means what is given. They say in this structure, I am again writing here BH whole 5. Okay, let's say this structure. Okay, BH whole 5 and minus 2. What we are adding? We are adding just 2 electrons. What will be the change? BH whole 5 will be same. 2 electron we are adding, it will be 4. Minus 2 electrons are there, minus 2 will be added, and it will be 4. So the structure will be minus 4 by minus 2, and it is 2. Now it will be nido, right? So the second case structure is nido, and the first case structure is closo. It is simple. So 1 will be the correct option. See how easy the questions are. All are CSIR-NET problems, and the interesting thing is for the each session actually for CSIR, let's say June or December, many questions actually, not one question, 2 to 3 questions we can find out from this. Okay, so these are very important, and I have shown to you the trick also by which you can solve the shape actually in a good way or in an easy way. So hope you have understood this session, and please practice more. to have a good idea about it and to solve the question in a more efficient manner. So I will see you in the next session. Thank you.